Hey everybody, welcome back. OSPF, our third routing protocol. We've done RIP version 2, we've done EAGRP, both distance vector and advanced distance vector. Now we come to OSPF, a link state routing protocol. What does that mean? Well, remember that EIGRP was an advanced distance vector, but it had link state properties by creating those tables. Well, OSPF creates those tables, creates a neighbor table, all right, has a topology table, has a database table. Obviously, every routing protocol has a routing table, okay? But it also, that database makes it special, and the hellos, because once it calculates using the shortest path first algorithm, right, or calculation, because it uses the Dijkstra algorithm, once it converges, it finds out about everybody. Everybody has its adjacencies together. Everybody knows about everybody. Now it keeps neighbor relationships using hellos. Those hellos in OSPF have to be the same with the adjacent router, with the neighbor router, the router that's connected to it. Just so you can understand what I'm saying. With EIGRP, that wasn't the case. That wasn't the case. The hellos could be different, but not here with OSPF. OSPF is very finicky, very finicky. All right. So yeah, it uses the Dijkstra. You can look that up if you want, so you can learn the physics about it. All right, we use cost instead of metrics or hop counts. OSPF has no limitation on hop counts. All right, it has none, zero. It can have, and is based on areas. So you can have from area zero up to 4.2 billion areas. All right, 4.2 billion areas. And just to give you a little something, all right, once you get that high in areas, all right, into not even the hundreds, the thousands or the hundreds of thousands, you're not going to say, hey, I'm in area 1,265,368. You're not going to say that. You're going to convert that into an IP address. So you can actually use a IP version 4 address. You do the conversion, you can change the area into that. All right, and that's normally what happens. But it is based on areas. There are not limitations, but you as a network engineer should think, well, the more people I have within this area, the more routers I have within this area, it could be an issue because one link after the convergence, everybody knows about everybody. One link goes down, the shortest path first calculation has to do the whole area again. So a lot of overhead, a lot of CPU usage with OSPF. It also uses a process ID number, but it's a local database number. Local database number. It has nothing to do with anybody else. It's just to maintain that database. All right. And we'll be doing these two types of configurations, which is a single area, which is a contiguous area, just like an autonomous system. Everybody shares the same routing table. And a multi-area, where you all have routers in different areas, or I should say really interfaces in different areas. All right. And we'll talk about definitely and do a lab with designated routers and backup designated routers. Now, like I said before, no limitations on how many routers. But again, you're a network engineer. All right. You have to make smart decisions. You're not going to fill up your VLANs. Let's say you segment your VLANs in your LAN, okay? And because you want to be more efficient so traffic can travel faster. But now all of a sudden you have 200, 300 people in one VLAN. You don't want to do that. Okay? You don't want to do that. It's the same thing with areas. You don't want to fill up your areas where it's like humongous. All right? Hello and dead timers. There you do a show IP OSPF interface, you'll take a look at those timers. They're there. Hello and dead timers. You'll see them. Okay? They have to be the same. So it sounds like a question that you may see on the test. Okay? So hellos and deads and neighboring routers must be the same. Must be the same. And in order to create a neighbor relationship, that has to be the same, or else it won't. Creates the following tables. I told you already, routing, neighbor, and database table. All right, and here's a little bit about OSPF. Don't freak out. These are just abbreviations for those of you that are abbreviation aficionados. But you need to know them because people talk that way. LSDB, link state database. All right, the data structure held by OSPF router for the purpose of storing topology data. That's what the database is for, that router ID, right? Then we have the shortest path first, right? That is the algorithm OSPF uses to analyze the link state database. Link state updates. That's how we get the updates of our neighbors, right? We have the name of the OSPF packet that holds detailed topology information. Link state updates, when we're creating neighbors, say, wait a minute, I don't know about that network. Well, hey, let me send you a link state update, and I'll tell you about that neighbor. LSUs. LSAs, there are many LSAs, and I'll be uploading reference material so you can take a look at all the different LSAs that there are. There are link state advertisements as you're going through your initialization phase, and we'll talk about that, and you're becoming neighbors. One of the things that will be sent to you are LSAs, the name of class of OSPF data structure that holds topology information. There are different types of LSAs depending if it's coming within your same area, right? Within your OSPF area is an inter area, is an ASBR, right? Exterior. So you have from LSA 1 all the way to LSA 11, all right? So they're all different ones. An area, a contiguous grouping of routers and interface. You're sharing your routing table. And then an ABR, that is an area border router. Area 0 is considered the backbone area. That is the first area that you have to make sure comes up in a real world scenario. In a lab, you can do whatever you want, but area 0 is the backbone area, okay? And everybody must connect to area 0 because area 0 updates everybody else. Real world, all right? So I'll be an area border router connects directly to area 0, all right? Backbone router, okay, boom, any router connected to that. An internal router, a router that has an interface connected to only one area. That makes sense. Internal route and one area, making the router completely internal to that one area. That makes sense. And then we have a DR, a designated router, and a backup designated router. Now, we'll be talking about it, but remember, a designated router and a backup designated router exists only in OSPF. It's an election process. And you'll see that mainly in multi-access networks or broadcast domain type networks or non-broadcast domain networks such as Frame Relay, which is a multi-access network as well. You'll see BDR and DRs or designated routers and backup designated routers in that particular topology if you have it and you're running OSPF. The election process, all right? Now, the election process for those guys is I will choose to be the designated router if I see the highest IP address on any physical interface unless there is a logical or a loopback virtual interface configured. So if it sees a virtual interface, a loopback interface, which is not a real interface, it says, hey, I want to choose that. And we'll see that when we do the lab, all right? Or you can manipulate the election, and you'll see how by changing the priority numbers. Cisco is really, leans more to or likes that you hard code the router ID, that will trump everything. All right. And not lastly, but one of the things that we're going to do is authentication. All right, type 0, obviously, no authentication. Type 1, plain text, we don't want that. So we'll be doing type 2 authentication using message digest. All right, and then here's the configuration. And it's very simple as you go through it. And again, you'll have this. It's basically enabling the authentication on the interface, telling it you're using message digest, and then you create a key, which can be no lower than 8 characters. And then you go into, we'll be doing area authentication. So then you go into router configuration, and you say area authentication or area, whatever area it is. It's going to be a multiple area. So let's say area 2, I think is the one we'll do. We'll see. Area 2, and then we'll do authentication, and then you see message digest. And that's it. The only thing is careful when you're doing this particular lab, because if you do it on the wrong interface or you're in the wrong router, because once you do it on one router, that's going to go down. So when you do authentication and the other one doesn't have any authentication, they're not going to talk to each other. All right. Now, requirements to create neighbors. This is important. All right. Must be in the same subnet. Hello. We know this. Must be passive on a connective interface. Okay. Must be in the same area. Yes, we know this. All right. Hello and dead timers. I told you that. The router ID must be unique. Every router ID, and what is a router ID? It identifies a router's name. The router ID is a router's name in an IP address format. That's what the router ID is. Okay, so it will always be unique because everybody has a unique IP address. Must pass neighbor authentication if you have it, and we will, so it has to pass. and K values, that's only in ERGRP, so it has nothing to do with it here. All right. And here let's break this down. Let's break this down. The first thing is hellos are sent from router 1 to router 2 as an example, right? And this is considered a down state. This is important. This is down state. Then hellos are received in router 2. Hey, I'm in an initialization state. All right, I got a hello from my neighbor. I'm going to reply to him. Now we're in a two-way state. Two-way state. And then routers begin to exchange their link state database information or just database information. And that's called the exchange start state. And then they acknowledge that they're LDBs or LSDBs. That is the loading state. Then they say, hey, give me a link state request. I request your information. He says, okay, let me send you some link state updates. All right, and then one router at a time, sensor updates, what have you. And then once all this happens, it says full state. You'll see full loading done. Great. Now OSPF can begin the shortest path calculation. This is why I'm telling you this, that the processing power is a lot. It's a burden on these particular routers when OSPF. So you got to make sure that when you configure OSPF that you have beefy routers, how much traffic is going through them, and if you are going to have a multi-access network or a broadcast network, that you're going to have a designated router and a backup designated router, that you choose the beefiest router to be the DR. Why is that? Because the DR, everybody updates the DR through the multicast address of 224.0.0.6. And then he will update everybody else through the 224.0.0.5. All right, that's the whole reason, because that designated router picks up everything. That's why there's a backup designated router as well. But when you look at those, they'll have those different stages. Once you're doing that, it'll stay, I believe, if I remember correctly, is at a two-way state. Those that are not DRs or BDRs stay at a two-way state because they don't complete this process, because they're sending the information to the DR, and as the DR, they will send everybody that information. But this is OSPF. There's a lot to OSPF. We'll be doing a couple of labs in here, all right? And you'll get very friendly with OSPF. It's not that difficult. Remember this, the CCNA. We'll be doing basic OSPF. We'll look at the DR, BDR. We'll do multiple area OSPF. So we'll do authentication. So no big deal. It'll be fun. It'll be easy. So let's get started.